Okay, folks. Let's start. So today's lecture is on legged locomotion, and we're going to do it in three parts. So the first part will be legged locomotion for quadrupeds. And here, the leading approaches now are all based on reinforcement learning. And I'll talk us through those. After that, we will have work on learning to walk for humanoids. And Ilya is going to give a talk on that. And this will end up being a bias sample. The first one is also a bias sample, very much towards Berkeley work. And then the third segment of today is basically the MPC trajectory optimization kind of approach, which Boston Dynamics has followed. And for that, we are going to give you links to some videos and so forth that you can watch. So I'm not going to be able to give the lecture all the way to the end because I have to get on the plane to Germany for Coral. So, okay. So let's start. So roughly 40 minutes on quadrupeds, 40 minutes on humanoids, and then homework is you spend 1.5 hours watching videos on the Boston Dynamics work on Atlas and so on. Okay, does that make sense? Okay, so let's start with learning to walk for quadrupeds, and we'll start with some examples. And I think of this as like the one of the first really big success stories for learning in robotics in the modern era. I mean, okay, because serious people, I mean, there were papers that were written about legged locomotion with learning and so on, but the serious work was all, Boston Dynamics, MPC, that kind of work. And what changed was really two pieces of work. The first was from ETH Zurich, from Marco Herter's group. So they led here. They were the first ones to show very effective training of quadrupeds with reinforcement learning. And that was followed by our work, which was, I think, even more purist in terms of being purely based on reinforcement learning with no gate priors and so on incorporated. So, so first, let me just show you some results of this quadruped walking. So this is a paper which was presented in 2021. So this is now like 4 years old. And this paradigm now has been replicated in many labs. So at this point, like it works. And what's notable is that this is just one policy. It's exactly the same policy. Okay. Whereas the style in the people who build MPC controllers is that they build different controllers for different kinds of terrains, and then they have a way to switch among them. And here is locomotion and navigation. So now you do have a camera. So far you had a blind robot. Again, it knows nothing about the environment. What it sees is what it uses. It's essentially got a local search for street stores. Okay, so the way I'm going to take you through this is in stages. This is more or less reflecting the history of this work. We're starting with what was the first version, what was the second version, what was the third version, and so on. Okay, so this is training with reinforcement learning in simulation. And I mean, the technique we developed for this is called rapid motor adaptation, and this is led by Ashish. This was his PhD thesis. So, so the initial training was reinforcement learning and simulation. Okay, and in simulation, you have this legged robot walking, and what is important is that you have sufficient variety. So how do you ensure sufficient variety? You need to have sufficient variety in the terrain. And the way that is ensured is by this fractal terrain. So you have ups and downs, but some ups are high and some ups are smaller, and so forth. So you get a very huge variety of terrain with this kind of synthetic terrain. So you train in simulation. Uh, and what's noteworthy here is that walking is a particularly good example here for the reinforcement learning paradigm. Why? Because in the reinforcement learning paradigm, it's basically a way to solve the optimal control problem. There is a cost function, and we are trying to find trajectories which optimize, right? So it should be easy to write down the cost function. That is important. The cost function for making an omelette is not so easy to write down, whereas the cost function for walking is very easy to write down. What is that? Basically, go forward, be smooth, use minimum energy. All right. So, but with these a priori considerations, you can write down a cost function for walking, and then reinforcement learning is just a technique for solving the optimization problem. I mean, you could solve it in other ways, and essentially the Boston Dynamics way is another way to solve that optimization problem. It's just the difference is just the technique. Okay. So I want to now state some of the philosophy, which is that we took these as starting assumptions, which is that unlike past work, which was very much gate oriented, that the way you design controllers for gates, so walking, running, etc. And gates are periodic movements, and these have been popular in robotics and motor control for a while. So this paper by Hildebrand lists the gates for various four-legged animals. Okay, so at a slope, so they're like pace, trot, walk, gallop, things like that, and they all have to do with the pattern of footfalls. And these were also popular in biological motor control because this suggests a fairly easy way to implement. Because what you do is you implement pattern generators. So pattern generators, so essentially you have some neuronal circuit which is driving each leg. And basically you can have exactly the same program, the same sequence, just shifted in phase for the different legs, right? So it gives sort of a neural economy because a fairly small circuit can achieve this behavior. And in fact, these pattern generators have been found in many species. And it's not just for walking. I mean, a fish swimming or a bird flying, right? You need to have this pattern of essentially some periodic movement of the wings or the fins or whatever. So these ideas are kind of old. This is a 1987 paper here. And so the first, I think there were legged machines before Mark Ray, but I think people in Ohio had tried to build a six-legged walking machine. But really the first really big successful effort, which got a lot of attention, was the work of Mark Raybert, which is kind of mid-1980s and 90s. And he's very much influenced by this pattern generator point of view. And if you and this is a point I need to make repeatedly. We all tend to think with, oh, what can we do today, and what were these people doing at that time? And you feel, oh, why were they doing such simple stuff? Why were they not doing walking robots? Okay, the way I showed you 5 minutes ago. So you always have to remember, in any area of AI, the techniques which we could use in 1980s and 90s were dictated by the computing power available then. So the computing power follows Moore's law. So you normally hear of Moore's law in the forward direction. But to have sympathy for all these old-time researchers, such as like Mark Rabert or me in the 1980s, you have to think of Moore's law backwards, which means that we had to make do with computers which were 100 million times slower than today. And the fact that we could do anything interesting, you guys should be appreciative of that, right? Because we had computers which were like a million times slower, 100 million times slower, right? Something like that. Okay. So that's why anyway, this is Mark Rabert's work, which is what I think this paper is 1983. And he was in fact not even building four legs. It was like a one-legged machine. And it is like in that era with some hydraulics and not electric, it was some big noisy machine which is like jumping up and down. You can probably find videos of that somewhere, which are fun to watch. Okay. Anyway, that's 1980s. But where are we now? So when we were doing this work, it was already close to, it was 2019, 2020. And at that point, the hardware situation had become pretty good because there were many groups which had developed good, robust hardware. And in fact, commercially, it was available. So we bought this robot from Unitary, which was available at that time. And we preferred it to something like Spot because we had access to the low-level controllers. And Unitary, in fact, also was selling these robots which were much cheaper because the previous generation of robots, essentially, you're talking $100,000 or more, whereas Unitary had this robot for $10,000. So cost plays a role in how quickly some stuff gets adopted. Okay, now what do we know from observations of human children growing up? So these are some pictures, but they're also videos. So these are just like videos that, for example, parents collect when their kid first learns to walk. It's okay, well, not the bottom two. Karen Adolph, Professor Karen Adolph at NYU has done a lot of research on this, and I recommend her papers to you. But this is the figure which I think I've shown in a previous lecture, but let me replay it. So this is how this girl is learning to walk. There is no gait here. There is no running gait here, no walking gait here. She's taking steps, sideways, forwards, backwards, right? And that's what we need to provide the ability for. So what the starting point for Deepak's work was, we said we are not going to program in any gates. We're going to have everything emerge with reinforcement learning, because clearly this kid is not starting out with a pre-programmed gate. So that was a distinction with respect to the dominant, in fact, the first big success of reinforcement learning for locomotion, which was the ETH Zurich group with Mark Oetter. So they start with a gate, and then they learn a residual policy on that with RL, whereas we made no such assumption. Okay, so I think this is a repeat, no pre-programmed gate. So this is like our slogan. We are going to follow this. Okay, next the approach is to train a policy in simulation. Okay, reinforcement learning, so that's all standard. Well, the notation here is X is the state, A is the action, and action here refers to joint angles. Okay, desired joint angles in this case. Now, there is a trick here which was used by the Marco Hutter group and was proposed by Vladlen Colton and Philip Cranbull in another paper, which is train with privileged information. So reinforcement learning is hard because it's a search problem, and then you have to find solutions which work in many different parts of the space. And to avoid the network from getting confused, it's good to give it some guidance. And the guidance here can come from ground truth knowledge of properties like mass, center mass, friction, terrain height, and so forth. So this is privileged information which is available at training time. And you can use that, okay? And in fact, what we can do is we can take that through an encoder. So that's basically compressing it, right? This might be like 20, 30 parameters, but we can compress it down to 5 parameters, 8 parameters, something of that sort, okay? Uh, and what you do is that you are conditioning the policy on this latent variable. Now, this is, I think, a cool idea, because what this is saying is, I don't need to have exactly the same policy for every situation. So the policy for walking on flat ground versus policy for walking in sand, policy for walking uphill, downhill, these policies can be different. Whereas traditionally you would design different controllers. Here these policies can be different because they get this Z input, which is capturing the situation in these different cases. And the Z is going to come from this encoder of these environmental parameters. Okay, so far so good. So now you can have one controller which is like the union of all the different controllers, because the Z is doing some kind of soft switching. Okay, so we call this the extrinsics. Okay, what's the reward function? So this is essentially an optimal control problem, and reinforcement learning is solving the optimal control problem in a certain way. And what are you minimizing? You're minimizing, essentially, you don't want to consume too much energy. You want to not, be smooth, move forward. Okay, it's very straightforward. There's no hackery here, which was what people end up doing in manipulation. So one of the reasons why reinforcement learning has been less successful in manipulation tasks is because just specifying the task is much harder. Okay. Okay, so now we have trained this robot and it has fallen a lot, but then it learns to walk. Okay. And then, and now we wanted to walk in the real world. And and this is where this technique, which we call RMA, rapid motor adaptation, comes in. And this comes down to this problem of what is the Z. So at training time, you know the Z because you have this encoder which has access to privileged information about the terrain and as well as some properties of the robot. But at test time, I mean, there's a blind robot walking in different terrains. How does it know? This Z is not known. So how do we? So the idea here is, let's run another neural network, which is going to try to estimate the Z. And this other neural network, the way it works is that it has to make use of some bigger temporal history of the movement. So why is that reasonable? Well, when you're walking on ground, on some ground, you're going to apply some forces and torques and so forth, right? Now, the consequences of that will vary depending on the kind of terrain. And that gives you a signal of what kind of terrain you are in. So, so we have to estimate this online, and this is done by this neural network called the adaptation module. So both of these are like small networks. The base policy is a small multi-layer perceptron. The adaptation module is another small network. I mean, so what this is doing is it has access to this temporal history, so 50 steps worth. And with that, so it knows what is the state and what were the desired actions. And from that, it's trying to estimate what situation you are in. And this training of the adaptation module can be done in simulation. So in fact, training this is a supervised learning problem, because you have a Z which you can estimate from privileged information with that encoder, and now that becomes the target for training. So that's what is indicated here. So phase one, you train with privileged information that you only have available at simulation time. In phase two, you are preparing for when you are going to be working in the real world and you don't have access to all this privileged information. And you do that by training this adaptation module. And this is a supervised learning problem, much easier. We know in machine learning, the supervised learning problems are much easier than reinforcement learning problems. So this is easy, and that's what is shown here. So 3 different modules are being trained. base policy, that's your essentially your RL, right? Okay. Environmental factor encoder, it's essentially the features of the, like these some 25 parameters of the environment compressed down to some 5 or 8. And the adaptation module is a network which which has the temporal history. So you could implement it with an LSTM or whatever, which has some temporal history, and then it tries to predict the C. Okay, and that's it. Now you're ready to run this in real time, and then we get this policy, one policy which works in all settings. Okay, I think we have seen that before. Analysis or adaptation module. Okay, so this is supposed to help you understand what's going on. So I think so. The experiment is there's some olive oil being spread on a mattress with which is covered with a plastic sheet, and then let's look at the dog. The dog's legs also have a plastic sock. So you're trying to make the job hard. Plastic on plastic with oil. Okay. And then as the dog walks, what's happened? It dips and then it recovers. Let's watch it again. Yeah. So, I mean, if you think about it intuitively, when you are walking on slippery ground, like on some icy surface versus walking on dry ground, you walk slightly differently. You walk more carefully, right? Okay. And that's what we want the robot to do at some level. Well, but how do you as a human know what to do? Well, you have eyes. So you look and you say, this is icy ground, and this is sand, and this is a flat road, and you change your strategy. This robot is blind, so it can't do that. So what can it do? It has to infer from its own past history. And its own past history is it commands some actions, and then there is an actual state change. So that's what's going to happen. And the way it's going to improve its performance, the way it's going to adapt is by the estimation of Z. So as it moves and it's on the slippery ground, it estimates the Z. And once it has the correct Z, that's an input to the policy, and the policy will change. No, not exactly the oily surface, because we just train it on a fractal surface with varying kinds of parameters of like friction and so on. So there's never exact same circumstances. That's not possible. What you need is something which is similar to it. Okay, and then it has to work. So because we cannot possibly create all the possible physical conditions that exist in the world for walking, right, in the simulator. But what you need are equivalents. So my model for this is metamers. Metamers as in color. So in color, or in color vision, what happens is that there can be two different spectral distributions of light which give rise to the same color response in the three types of cones that we have, right? And so there can be two lights which are not the same, but to the human eye they appear the same because their projection on the response functions of the three cone types are exactly the same. So that may be something which helps you to think about this. So here, what's happening is you look at these variables Z1, Z5. So these are some of the components of that Z vector, which is H-dimensional. And you'll see this red curve, which is high, and then it becomes less, and the blue curve at the bottom, it goes the other way around. And that's essentially happening as the robot is struggling. So let's see this. So it's struggling, and then the Z value is getting changed, and then the new Z is applied to the walking policy, it starts to walk correctly. And then here's something else, which is the robot is, and you throw 5 kgs. This 5 kg is a big deal because this robot is 8 kgs. Okay, so therefore, so what happens here again is in slow-mo. Again, some variables, in this case Z2 and Z7, they sort of capture how the situation has changed. And then the robot starts to walk better. And in fact, if you look at this variable called knee tau, which is kind of in the middle, essentially that changes. So you're applying greater torques, which you need to because you're more mass to carry. And okay, so this is so we have so now you can take do the so now you do the in research you should do experiments to better understand what you did, and ablation studies are a canonical example. You change some, you delete some module and see whether how it works. So this is how RNA works. But now suppose you did not have this adaptation module. Okay. Okay. And here's another one. So this is the mattress. So note again, there was no mattress in the training, right? It's just that there was something equivalent to it because of the variety of terrain. So this is how the robot walks on the mattress, and without adaptation. Okay, and then it works better than A1 controller. But anyway, I think I can do good fine. All these stories have the same ending. It's the RMA controller which works and the other one dies. Okay, so okay. Good boy. Okay, 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 okay. And then you can show some results. So I won't go through all the numbers, but I mean, uh, but the impressive part really is this adaptation, I think. And then subsequently, this algorithm has been applied in other settings. Okay, and then there are some numbers which I'll skip. Okay, and then various. So we did a lot of experiments on uh, RMA without the adaptation in different settings. Some experiments are done in synthetic conditions, some are done in physical conditions. So good research requires doing a lot of experiments, and they should be and both done in simulation because you have more control, and you should do them in the physical one. Okay, okay. So that's version 2. Version three is how do we get it to walk at different speeds? Okay, it turns out this is kind of trivial. Okay, why is it trivial? It's trivial because one of the terms in the loss function is walking at a you get more credit for walking uh, at the desired speed. So when you're walking very slow, you can get more credit by walking faster. But once you have hit the desired speed, you don't get any credit for walking faster. So you can just train controllers for different desired speeds. You can also train controllers for different angular velocities. So this way you can get the robot to rotate. And then you can distill it all into one common policy. So sometimes this is a good trick. You train different versions because RL is finicky. So it's easier in a more restricted setting. You will make it work and then you distill it. Okay, and then that's it. And then here are results. So different desired speeds. And now what you will see here with all these solid blocks. So it's right front, left front, right rear, left rear. Okay, so those are the 4 rows. So when you have it filled in, that means that the foot is on the ground. When it's white space, that means that the leg is in the air. So when it's walking slowly, most of the time, most of the feet are on the ground. As you go to the extreme right, you see that the amount of time on the ground is reduced and the amount of time in the air is increased. And these are the gates that you get. Okay. Oh, sorry. I should have let it go through. So now it's really happy. Okay. And then why did we get different gates? Well, this is the point of this paper that turns out that different gates are more energetically efficient at different speeds. And we talked about this earlier in the course with respect to humans for walking and running. So the same is true for horses, and the same is true for us. And then these are some results. So it's kind of robust in these different functions. Anyway, I'll skip this. Okay. Now this is, yeah. For what purpose? Some, yeah, some duration in the past. How long should it be? Basically, on the order of a gait cycle. Yeah. I mean, in walking, there's a very natural unit of time, which is sort of the gait cycle, right? In that, you will get all the information, and then it should be repeating. So a couple of seconds. Yeah, so it'll be if suppose you have, yeah, so you put in as many time steps as needed for capturing the. I mean, your control is operating at a certain rate. So okay, so there's some subtlety here which I didn't go into, which is this RL policy doesn't operate at 1,000 hertz, right? It's much slower because there's a lot of compute involved. So it's operating at a slower rate than the PD controllers at the level of the joints. So those are operating at more like 100 hertz or 500. I don't know the exact, don't remember the exact number. Okay. And so that's the policy. And this adaptation is actually operating even slower. Okay. But it it it's it can be slow, but it cannot take 1 minute. In 1 minute, you will fall. See, humans, we recover. If I slip a little bit, then I recover. I move my hands and I recover. What's the time scale of that? It's on the order of a second. Okay. If I took 10 seconds to reorient my body, I'll fall. But I do not need it to be recovered in 0.1 second. I mean, it's just, I mean, physics. That's what is happening here. Okay, this is combining navigation with locomotion. And this turned out to be quite straightforward. So we have this policy which you can say go in a particular direction. So this is now a hierarchical controller. So the lowest layer can do the walking in any particular direction. And what you need to do is to tell it which direction to go. And the direction in which to go is given by essentially what's free space. And you can use the ideas from the navigation data. So it's, yeah. So this is just classical ideas for obstacle avoidance. I mean, you can, so this is why navigation is not so hard. It's really looking locally, where is free space, you go in that direction. You do not need a complete map of the environment. Okay. Okay. And then, okay, here. Okay, here's some little trick, which is that when you are on sticky ground, then you should walk slower. And essentially, the robot, when it's on the planks, it walks slower. Okay, how do we achieve that? It's pretty easy. What you do is you have an estimator for the probability of a fall, which you can train in simulation. And the probability of a fall is higher when you're walking faster, right? So the robot starts to walk. It's always running this estimator of the probability of a fall. And this probability of fall has gone high. So you start to walk slower, and then the probability to fall comes down. And that's it. And that results in safe walking behavior. And it's, I mean, something that we would do, right? Okay, vision. This is what a vision model does. Okay. So what do you think went wrong here? It's glass. It's transparent. So the vision system doesn't see the glass. Okay. Thanks. So this works much better. Why? Because proprioception means that you're using the joint angle. So when you're trying to move and you are not moving, you know that you must have hit some kind of a wall. So
seems to continue that pattern even after it leaves the.
Yeah. Okay, and then fall predictor, collision detector. Okay, so okay, it's going to say vision and proprioception better than only the one. Okay, let's see what it does for vision and proprioception. I mean, this exact behavior is not programmed, so it looks pretty clever, but it's obvious. It's just looking for white space. Okay. 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 I think I'll get more video, but we tried it in lots of places. It works. Okay. Now the last part of my quadruped talk. Oh, I think I was. No, it's okay. 40 minutes. I'm only 30. Is using vision for movement in the obstacles in the vertical domain. So think of obstacles as being in the horizontal plane. So there you just rotate your direction of movement, right? So you just use yaw. You move in a different direction. Now, what about the obstacles which are in the vertical direction, like stairs and so on? Now you have to change your movement in the vertical direction. Okay, so that's what this paper is about, and this is the last bit that I want to talk about. And okay, this is just saying who else had worked on locomotion. Why do we need vision? We need vision for these difficult situations. Okay, so here I want to make a point which is worthwhile, which is what's the classical robotics way of doing it and what was the way that we developed. So the classical robotics way of doing it is build a map. That's what classical robotics people do. They believe in state estimation, and the way the vision is used is you build a map. So therefore, you've got your robot moving, it's got a camera, you try to build a map. And the map can be built in a more detailed way, not just 2D, but also 3D. Okay, and what's the problem with that? I mean, in theory, this is fine. In practice, it doesn't work so well. Why does it not work so well? Because there's this, and you discover it when you do real world experiments, is that your robot and camera are shaking, right? Your robot is shaking, your camera is shaking. What that means is that each individual data that you have captured is good. But when you try to fit it together, you've got all this noise because from the pose, the rotation and translation of the camera from one frame to the next, I mean, that's taking place and you do not have an accurate estimate of it. So you put it all together, what's going to happen is your resulting map is going to be noisy. Okay, and then, so that will happen in the real world. And now what do you do in your simulator? Well, in the simulator, if you don't do anything, you're going to be in trouble. So what you do is in the simulator, you add synthetic noise to your maps. And this results in not so good behavior. It results in suboptimal behavior. So yeah. So anyway, so if you want to see the comparison here, you can look at the work from Marco Hutter's group, where they use this map type approach. And so they were pretty successful. I mean, you look at all their deployments, but we wanted to show off, and we wanted to find a setting which was hard enough that their technique wouldn't necessarily work, but ours would work. And this is okay. It's the same policy, but the impressive demo is this one. Lots of people can go up and down stairs, but this going on, okay. And note that it doesn't know the environment in advance, and you can rearrange the tool. Okay. Okay. So this is an easier version of the problem. Stairs is easier than going on the tools. Okay. I think I've shown this video a million times, but so okay, how you train this system. So again, idea of privileged information is good. So at training time, you give the robot access to the depths at a bunch of points near in the neighborhood of the robot. And it uses that for training. And the philosophy is a little bit like RNN, a little bit like RMA, but now capturing the geometry of the environment. So the geometry of the environment is being, so there is this Z variable, which is the latent variable which captures some of the physics parameters. Gamma is a latent variable which captures some of the geometry parameters. And that's essentially what's the information you need to know for foot placement. Okay. By the way, this foot placement that we have here, it emerges in this part of this policy. The more classical way, like the Boston Dynamics type of style, what they would do is they will first be thinking about foot placement. So very consciously you figure out where to put my left foot, then to put my right foot. So there's like a planner which is figuring out foot placement. And then there is your MPC controller, which is executing on the movement of the body. And something about this seems wrong, right? If I spent my entire life when I was walking, planning my foot placements, okay, I mean, I do all my thinking when I'm walking, and it's because I'm not using my planning capabilities to figure out where to put my next foot. Okay, so anyway, philosophically, it seems this planner approach is wrong. Okay, in reinforcement learning, we can do it differently. You try, I mean, as always, you have a lot of variety in your terrains, blah, blah, blah. Okay, I'm skipping the details here. You start with an RGBD camera, and then is the spirit of RMA, but extended not to capture these geometric parameters of the terrain. And you look, I mean, I think the cool part is that the rear foot lands up not on the ground, but on a stick. I mean, of course, you have the information in the front, but you have kept enough of it. So I think Boston Dynamics Spot is being tested in like say, millions of hours of walking. But I, I don't know if they have a demo of walking on the screen. So if they do, let me tell you, let me know. Okay, and then we also claim that this robot can climb up. So it figures out this trick of lifting its leg off on the side. And this is the power of RL. So you wouldn't get this with imitation learning. You need in reinforcement learning can discover new solutions because it's search. And then so it really tries hard. Look at this. I think this on the right you'll get some impressive results. When I see this dog, I really get this sense of it is trying hard. It's of course just a computer program. So we anthropomorphize. Map free. Okay, so previously our slogan was gate free, then our slogan was map free. So map free, gate free. And then, oh yeah, numbers. Okay. And then here I have to, so at the end, I have to end with bloopers. So this is a blooper. And this is, that was supposed to be another blooper. Let me see if I can get it to upload. So on these tool type things, I think in 10 tries, word on. Okay. It worked like 9 out of 10. So this is, I think, that failure. And I'll end here. And now Ilya is going to tell you about humanoids, which is a harder. So I think quadrupeds are solved. We can do quadruped. I mean, people have done work after that on parkour and so on, but it's the same machinery. I think the ideas here are general, they're robust, they work. Okay. Humanoids is harder because walking on 2 legs is harder than walking on 4 legs. So Ilya will entertain you now. Let's give people a 2-minute break, right? But you can plug in. Okay. Let me exit now. Yeah, there's a Zoom session which you can get to from the website. Yeah. So to get the right display, first log into Zoom, then put your yeah. Let's see the right view.
Sorry, do we have the Zoom thing working? Maybe I need to chat. Yeah. Okay. Got it. Yeah.
It's good?
Yeah.
Okay. So you can take whenever you're free, then you can record.
Sure. Did you do the 2 minutes? Is okay?
Yeah, we are done.
Okay, so we've seen in the first part of the lecture, right, we've seen a lot about quadrupeds, right? And now we'd like to talk about humanoids. But I thought it might be worthwhile to sort of think about these two a little bit. So if you think about of a quadrupedal robot, right? You have this big body that has a lot of mass, and then it has four relatively light legs in comparison with the body. So so that means that essentially, as the legs move, it sort of impacts the body less. Now, in contrast, if you look at the humanoid, it has it's sort of it's bipedal, so it's easier to lose balance. It has heavy legs. It has a big, heavy torso with a lot of mass and inertia. And as you sort of move, you're moving that mass and inertia around, and you need to essentially, it's much harder to maintain balance. So that makes this problem considerably more challenging than the problem of quadrupedal locomotion. But nevertheless, there's been a lot of work in this area, and I'll show a few of my favorite examples. So first, here's this robot called Asimo from a Japanese manufacturer, Honda. So what's interesting is they've started working on this research program in the 80s, and they've sort of kept it secret undercover for, I think, about a decade. And then at some point, the Japanese government was sort of starting this big research effort on humanoids. They're like, oh, by the way, we have this thing, and it's pretty good. And of course, this is not their early version. This is one of their latest versions, and you can sort of see it's pretty cool. It could do a bunch of things, and it could work. And this is not the first development in humanoids in Japan, of course, but this was one that I thought was pretty neat. But then another reason why I sort of pointed out this one is because the walking in this case is based on this principle called zero moment point, or ZMP for short. So this is really an old idea. It was first published in the 1968, and it was sort of done purely computationally without a hardware proof. The hardware proof came later in the 70s in Japan. But it has been the basis of this Asimov robot, and it's, my guess would be also being used in the today's sort of latest and greatest humanoid efforts like, Figure and Tesla and so on. It's still sort of based on this technology largely. And what's the tell, right? So we'll give you these details so you can see, but basically the tell is this flat foot walking where one leg is always stable on the ground. So you'll notice in these videos that the robot is sort of always has one leg on the ground, and it's sort of doing a little bit of hip movements to correct for the rotation. And let's look at another Asimov video and sort of focusing on that, and you sort of really distinctly see this. And now, of course, coupled with some sort of obstacle avoidance, but focus on the gait, and you'll very clearly see this. And now, if you sort of, given this, you look at the, your Figure video, or your Tesla video, it shares some similarities with these classes of approaches, and of course they've been extended and improved and so on. But the basic principle is there. So now the challenge with something like this, right, is that you have this distinction between foot planning that Jitendra mentioned earlier and walking, and it's very hard to get really dynamic motions with something like this. But of course, we've all seen Atlas Dynamics videos. Atlas Robots videos from Boston Dynamics, and I don't think we can have a humanoids lecture without showing one of those. But what's really interesting here is that this is super dynamic, right? So like this robot is running around, doing parkour, jumping, going over obstacles, and so on. And super, super impressive, right? So like very sort of like completely a different league, and the step functioning capabilities compared to the previous video I've shown. And what enables this? Well, as Jitendra mentioned earlier, this is enabled by Model Predictive Control, or MPC for short. And this is something that Boston Dynamics has been sort of really pushing for a while now. And we'll, I think, include a few videos from Scott and other folks at Boston Dynamics on. And so you can sort of see, hear from the leading institute in this area. But this class is about learning robots, or robots that learn. So I think for the rest of the lecture, we'll focus more on learning approaches. And you might also ask, well, I guess once you see this, and sort of in the context of the quadruped work that Jitendra has mentioned, right? Sort of two questions pop out, right? Like, so the first question is, isn't this solved, right? This looks amazing. It can jump and can sort of go around. Like, is this it, right? Why haven't we seen robots in the real world? Why don't we yet have humanoid robots around us? And then the part of the answer there is that these approaches are really good in structured environments. So as long as you sort of know the environment, you have a very good sense of perception, you can sort of essentially recreate a map, then these approaches tend to work really well. But they struggle with generalizing and adapting to new environments or variations of seen environments. And that's sort of why you actually haven't seen very many videos of Atlas out being sort of in the wild, or really seen Atlas outside the Boston Dynamics office. And so that's sort of one. And then the point number two, or question number two, you might ask is, well, we've seen that quadrupedal robots are doing really great. Like, they can go, Ashish's robot can go basically anywhere. So why are these robots not there? Can't we just sort of rerun the same thing? And sort of the answer to that is a little bit more nuanced, and I think has a lot to do with the extra challenges of humanoid robots. But in principle, we should be able to have some sort of a learning technique that should enable us to get to the same level of capabilities, but with humanoid robots. And then so for the rest of this lecture, I'll show you some progress we've made towards that goal. So it starts with this work on real-world humanoid locomotion, which was a collaboration with a couple of groups here at Berkeley. And here is a video of our robot walking around Berkeley campus. So this is a digit robot developed by Agility Robotics. So it's a company out of Oregon. So we don't build hardware, as you might have guessed, but we purchase this off-the-shelf hardware, and then we develop our own software. So what you can see here is a robot that's walking and being controlled by a neural network, a single neural net that's running on board, and it's getting access to the proprioceptive state of the robot, and it's predicting the future actions. So it does not use perception. It's completely blind. It doesn't use LiDAR. It doesn't use depth. It's fully blind, and it's being and all of these videos are a single policy. So how is this achieved? Well, this is achieved through an end-to-end learning approach that's based on a transformer model that takes us input a proprioceptive history of interleaved observations and actions, and then it predicts the next action. And that's it. So here the observations are joint positions, joint velocities, IMUs of the base, and then the actions are the desired joint positions. So sort of this is very much in spirit of RMA, the Jitendra presented in the context of quadrupeds, and you can think of this as sort of being a slightly more end-to-end version of that, where but the principle, the sort of the philosophy, the sort of the things we want to achieve are very much the same and aligned. Now, like before, this is trained entirely in simulation. So here you can see thousands of different robots being simulated in slightly different terrains using slightly different dynamics properties. We train these robots on mostly gentle terrains, so it's sort of mostly flat with a little bit of slope and a little bit of these rough terrains. And then each robot is sort of also has randomized properties of its body, of its masses, frictions, and so on. And then the intuition is, if we can train a single neural net to control all of these different robots, then perhaps it will also work in the real world, because you can kind of think of the real world as being sort of yet another simulation. And that's kind of the hypothesis. So once we train the model in these terrains, we deploy it to the real world, zero shot. So we do not perform any fine-tuning on any updates in the real world. It's just being deployed entirely zero shot. And so in addition to sort of walking forward, this model can walk. This approach enables walking in any direction. So it's conditioned on these velocity commands that Jitendra has described earlier. And then, by supplying different desired commands, you can achieve walking in different directions. One interesting thing we noticed is this emergent arm swing. So a robot is sort of swings its arms like a human as the human is walking. And this is something that we haven't pre-programmed, but it's also kind of interesting. And, if you think of human walking, it's somewhat of a peculiar characteristic of, why do we swing our arms this way? It's not entirely obvious. And it turns out that this is something that has been studied a lot in various different areas, and there are various hypotheses for why we're doing that. But the one that seems most likely under the experimental data is that we swing our arms to preserve energy. So this is a really nice study from Stanford where they compared different walking styles in terms of how the arms are moving. And it turns out that essentially if you're swinging your arms in a dynamic and normal fashion, you save the most energy. And this was sort of extra interesting to us because one of our reward terms for training our model is to minimize energy. Now, of course, we don't have a causal relationship here that is indeed what causes this behavior, but it's an interesting observation. It's also an interesting, I think it suggests an interesting use of these sort of reinforcement learning models or computational models really to verify these hypotheses about human movement. Another really interesting behavior we've observed is adaptation. So consider the following experiment. We have this robot that's going to walk over a terrain that consists of 3 sections. So walking on flat, walking downslope, and then walking on flat again. So let's see what happens. So the robot starts by lifting its legs, then it transitions into this gait of sort of stepping slowly, and then it goes back to walking, sort of lifting its legs again on flat. Now, what's interesting is that we have not pre-programmed this behavior. This is entirely emergent. We haven't encouraged this in any way. We haven't specified this in the reward function. There's nothing really that tells the model to do this. It sort of emerges as a byproduct of training. And it's also, this was really nice to see because this ability to adapt actions based on context is really quite fundamental to human walking. And here is an experiment from human babies from Professor Karen Adol that Jitendra mentioned before, where you can see if the baby is sort of walking on flat ground, it doesn't change its gait. But now let's see what happens if we slightly change the slope. So now the baby changes its gait. So our robot's not quite that adaptive, but still adapts a little bit. Let's see what happens if we change it even more. So we can't do that yet, but you sort of get the idea. This really seems like a property that's very important, and I really recommend reading this work. It's really, really, really nice and sort of points out many experiments like this. But if we look at the experimental data from our experiment, we see a few interesting things. So we see that there are certain patterns of neural activity that corresponds to different features of the environment. So here, for example, this neuron 82 is just like really a unit in the network that we're plotting its response over time. So what we see is that the responses are sort of fluctuating more when the robot is lifting its legs more, and then they're fluctuating less when the robot is lifting its legs less. Then next, this neuron 108 is high when the terrain is flat and is low when the terrain is sloped. And then finally, in aggregate, if we visualize the neural activity of this model, we see that the activations cluster naturally into these 2 groups based on the terrain that the model is training on. So this suggests that these the neural representations of this transformer model are able to capture something about the environment that's relevant to walking. Now, we don't have a causal relationship that says that the model is indeed changing actions because it is able to do this. But it would be interesting that would be an interesting thing to study. But we do see that the representations correlate strongly with the changes in the terrain. Here's another interesting example of recovery behavior. So this is a little bit like the hip abduction behaviors we've seen in the case of the quadruped, where because the model first tries to perform a maneuver, it fails, and then in subsequent attempts, it changes its actions to swing its legs faster and higher to achieve the desired goal. So in summary, we've seen a fully learning-based approach for humanoid locomotion, and we've seen some really nice properties in terms of adaptation with transformers, and these things together have enabled us to deploy this controller to the real world. Okay, but so now we've seen results that were in the real world, but they were largely on gentle terrains. So they were sort of mostly flat, sometimes a little bit of slope up to a few degrees, sometimes some easy overground obstructions, but nowhere near as challenging as the results we've seen in the case of quadrupeds, which then really brings this question of, okay, can we extend the same approach to more challenging terrains, right? Like, could we do the same thing? Like, could we sort of, include more complex terrains in simulation, run the program for longer, and sort of get the model that can walk anywhere? So in principle, yes. There's no reason why this should not happen. But in practice, there are many challenges because the problem becomes harder. Terrains to simulate are harder. Reward functions become harder, and all of these challenges are mutually reinforcing, which sort of makes the overall problem harder. So we take a step back, and we ask, okay, can we take the same architecture but train it in a slightly different way? So concretely here, we study if we can train the same transformer controller but using sequence modeling instead of reinforcement learning, and we do this by proposing this framework that has three parts. So first, we need some sort of a data set in order to be able to train this model. Next, we have the model that's trained on this data. And then finally, when this model is trained, we deploy it into the real world. And then I'll discuss each of these three in turn. So on the dataset side, we essentially compile a large collection of walking trajectories that come from various sources. So we consider trajectories from our previous neural network controller that gives us full access to both observations and actions. We access the trajectories from a model-based controller that's a proprietary controller that we can only access the state of, as well as mock-up sequences of humans and videos of humans. So a few things to notice here. So one is that there's this distinction between sequences that have actions and sequences that do not have actions. And this is important because there is more information in sequences with actions, and actions are really what at the end of the day we care about and we want to be able to learn. And then the second thing to notice here is that the morphologies are different, and the sort of the accuracy of data is different. So in the case of the data that comes from the same robot, well, then the morphology is matching, and that's great. But in the case of data that comes from humans and videos, the morphologies are different. The pose estimation problem to sort of lift human videos into motion sequences introduces errors, and which in turn introduce noise and so on. Okay, but I'd like to highlight the internet videos data a little bit because I think that one's really interesting. So here you can see two videos of human walking or human running, and you can see reconstructions recovered by computer vision techniques developed by Jatushan, Shubham, and other folks in the lab. And you can see that they're not perfect. There's like a little bit of jitter, but they're sort of pretty good. And then you can use these trajectories to kinematically retarget the robot morphology onto the human trajectories. And these retargetings and these reconstructions aren't going to be perfect, but that's okay because our technique sort of does not require them to be perfect. We're not interested in mimicking these exact trajectories. We're interested in acquiring general purpose skills from the collections of trajectories like this. And because of that, we can tolerate noise, and it's okay if the data is imperfect. It's okay if the data is noisy. And it's sort of one of the big lessons of deep learning that we prefer scale even with noise over small amounts of data that's perfect. And then we have a way to train with all of these different trajectories in a unified fashion. Here are some results of this approach. So what you can see is a controller now that's exactly the same architecture as before. It has been trained in a different way and is deployed to the real world. It's here, in this case, spanning the different locations in San Francisco. And so you can sort of, it's still mostly on gentle terrains. Please.
More of the data from there.
Yeah, it was roughly equal. The data source is the most important, is the one with actions, of course. Other data sources help, but the one with actions is the most important one. I think it's sort of an open question to see, remains an open question to see how far we can push this by sort of really scaling the internet data sort of to a much larger scale.
Was it easier to get or less reward function, like I think when you combine them with data, so that then find that return? then you decided what to do this now, and found out like the videos are obviously scale a lot better than just the training in RL, but the problem in itself becomes easier when you're doing the dollars, like look at data.
So this approach has no reinforcement learning. There's no RL here.
Like in this RL, we got like the first and
Right.
yeah.
So what is your question?
Problem with like easier to get it from walks compared like to as a good RL.
Yeah, so this works. This is super scalable, super easy, super simple. Like you can train this model in half an hour on only 20 hours of data. In comparison, the RL model is very finicky. It takes about a day or two. So that's sort of that's the benefit we get from sequence modeling, and I'll get into trade-offs shortly. But then and another thing that's sort of nice is that if you carefully sort of look at the gate of this model and the one before, you'll notice that this one's slightly softer, and this becomes really clear when you run them in the real world, because sort of the noise is the tell. The audio really lets you distinguish these different policies. And one thing that we're really pleased to see is that the prediction error, that is the subjective, correlates pretty strongly with the walking performance as measured by walking metrics like velocity tracking and so on. Another nice experiment we did is we wanted to study to which extent can this model generalize to unseen behaviors. So we took a bunch of trajectories of walking forward. We trained the model on that. And then at test time, we prompted the model with walking backward, which was not seen during training, and the model can still perform those behaviors, which was interesting to see.
Question: how do you prompt the model to walk?
You supply the desired velocity command. So forward versus backward would be the sign. So plus 1 meter per second is walking forward 1 meter per second, minus 1 meter per second is walking backward.
Is that like an actual something that's into the model?
Yeah. So in summary, we've seen that we can cast the problem of real-world humanoid locomotion as a pure next token prediction problem, and that enables us to train with various sources of data, and gives us a model that we can then deploy onto a real humanoid robot and have it walk in different areas in San Francisco. Okay, so going back to the question you raised earlier, how does this compare to reinforcement learning? Right, there are trade-offs. So this approach is far more sample efficient and stable, which is really nice. So we can this sort of has all of the appealing properties of sequence modeling that we've seen really flourish in the domains like language and vision. But then the challenge, right, is that we cannot get new behaviors, truly new behaviors, because the skills that we can learn are limited to the skills that we have seen in prior data. So there's no free lunch. Really, the only tool that we have today that can give us something that's truly novel and truly new is reinforcement learning. But then it comes with all of these trade-offs. So then we really in this latest work we've asked if we can combine the benefits of these two different paradigms to see if we can get something better. And specifically, we propose an approach that consists of 2 steps. So in step 1, we pre-train the model with sequence modeling. So this is exactly the same as the most recent work I presented. And then the intuition is that even if this model is not the most capable one, it'll give us a good starting point for acquiring new skills. And the way we will acquire new skills is through reinforcement learning in simulation. So we first pre-train a model with sequence modeling, and then we fine-tune it with RL in simulation. So what's the intuition? The intuition is that even the robot that can only walk on flat ground should be more efficient in learning how to walk up a slope than a robot that cannot walk at all. Right, so that's kind of the intuition, and quantitatively this sort of matches what we observe in experiments, and we fine-tune it in simulation in a Mujoko simulator using various terrains. I'll discuss them a little bit later, and then again, same as before. Once it's trained in simulation, we deploy it to the real world. And we really wanted to see how good is this controller actually in real world environments. So rather than sort of handpicking a few different terrains. We really wanted to take it to something that's representative of the terrains that the humans would walk on. And one natural case of those are hikes. So we took this robot on 5 real human hikes, and we've sort of just completed them. In total, that's been over 4 miles of hiking. So you might recognize some of them: the Inspiration Trail, the Belgian Trail, and I'm only showing 3 here. And I'll show you some snippets from those hikes. So this was the Belgium Trail towards the very top. So this was about 1.1 miles of hiking. Took close to 2 hours. And the robot was able to successfully navigate these different terrains. Here's something that's a bit harder. So here we have a slope with loose and rocky terrain. And this is in the panoramic trail. And I think the video froze. But you can also see all of these on the website. But then, natural environments are one source of challenging terrains. Another source are man-made environments. And in that aspect, we're fortunate to be near San Francisco, which probably has some of the hardest man-made environments for walking. And we went to various steep streets in San Francisco, and we've evaluated our robots. So here I'm showing a few snippets from the Russian Hill neighborhoods. I'm showing the percent grade on the top left of each image. So to calibrate you, the ones that you can see in the top right, about 31% grade. So these are about the steepest streets in San Francisco. The steepest would be 31.2, 0.8, sort of a little bit less than 32% grade. So this is super steep, and this is hard for healthy human adults as well. Going up these streets, and this robot can sort of go up, can turn on the slope, can go down, had no faults on any of these, and it can sort of navigate all of these without problems. Let me show you a few videos of that. So here's one video of going up. So this is overlooking Alcatraz. You can see in the back. And here's one of those really steep ones. So here you can see the Bay Bridge. So this is the Broadway Avenue. And this is 31% grade. You can also see the cars. The cars are pretty sloped, yeah. Okay, so what's interesting is that we see that different gates emerge for different slope types. So whether the robot is walking on flat, is walking uphill, is walking downhill, it's using a different gate, and you can sort of measure that by looking at the joint positions of a couple of these critical joints over the gate cycle. And again, this is completely emergent. We haven't pre-programmed this or encouraged it in any way. And another thing that's interesting is that when we fine-tune this model, we only fine-tune it on rigid terrains. So only flat, slopes, discrete obstacles, rough, hills. So sort of everything here is rigid. There's nothing that's soft. There's nothing that's deformable. But then we deploy this robot on sand, and this is pretty deep sand. And you can see that the robot can still figures out how to adjust its movements to maintain balance and avoid a fall. We can also go through water. So in retrospect, this was a pretty expensive experiment, but luckily it worked. And yes, it's all of these are unseen, and it's really interesting because there's nothing in simulation that's simulating soft, deformable. It's all rigid. It's all entirely rigid, and it's conceivable that some combination of forces really simulate something that's a little bit like walking on rigid, but still I'd say that there is a big domain gap here. And
trying to compare not opportunistic and continuously. How about just sampling the continuously data, including opportunistic and do data mixed?
Yeah, we have not done that yet.
Yeah.
I mean, it'll work. The interesting thing is that if you were to sample your fine-tuned model, you put it back in pre-training, you would be able to absorb those skills very efficiently. But there would still be new behaviors that you wouldn't get. You couldn't learn to say walk upstairs that way, because that would be sort of something that's entirely new. So I think sequence modeling is really great at absorbing what's already in the data, but it is very unlikely to give you something that's truly novel and truly new. Reinforcement learning, I think, is the only tool we have for that. Please, Eric.
You're throwing up like these extreme slopes of the descent. Is the argument that like this is entirely in the mode of what was learned in reinforcement, or is just the idea that like the pre-training just helps you do more sample on quickly?
Yeah, so pre-training really helps you with sample efficiency. Is the main help. It's not only sample efficiency; it also sort of determines your starting point such that it becomes easier to optimize from there, and your reward problem is a little bit easier because you already sort of kind of know how to walk. But these behaviors are not seen even during fine tuning. So this is auto distribution. And then the sand example is pretty interesting because here we do an experiment where we walk on the tail first and then we transition into sand. And you know, as a human, you would expect that, right? As you're walking through sand, you need to exert more energy. You need to in order to lift your legs to the same position. And we see this here experimentally in a sense that if you look at the middle plot, you see that in both cases, the robot is reaching the same positions. But if you look at the third plot, you see that it's using more torque to do so on sand. And this is an example of dynamic adaptation to different terrain type. And the robot is very robust to external disturbances. And this is pretty hard because it's slightly sloped, it's uneven, and it can it gets this recovery behavior of sort of putting its leg in the back. Now to give you a little bit of context, what happened here is
but in training, did you supply these both kinds of systems?
We did. So this is not, Jitendra is saying this is not that surprising that it would be this robust, but it's sort of something that's pretty hard to get with, let's say, you know, traditional approaches, but also the sequence modeling approach that we described would have a really hard time getting something like this. But what happened here essentially is that the joystick of the robot malfunctioned, and then the robot kept drifting towards this lamppost. So I had to push it just to not run into a lamppost. This was not supposed to be an experiment to show, but it turned out that was the only experiment, the only video that we have of pushing the robot, and people want to see pushing the robot. So this is the robot. This is the video that we have. But what's interesting is that we also see that these neural representations of the model really capture the terrain that the robot is walking on. So here, if we plot all of them together, we see that the flat clusters with flat, trail clusters with trail, and so on. And we haven't pre-programmed this either. This is entirely emergent and happened as a byproduct of learning to walk. Now, Eric, to answer your question on sample complexity, so what we see is that that fine-tuning a model that's pre-trained leads to better sample complexity than training a model from scratch. And I say that this is part of the benefit. The other part of the benefit is that it also leads you to better solutions than training the model from scratch. And this is pretty drastic in a sense that we can now train these models train good walking models in about 100 million steps, compared to our previous work on reinforcement learning, which was on the order of 1 to 10 billion steps. And where does fine-tuning help? Well, it helps a lot on these uneven terrains, and it helps a lot with disturbances like pushing and slipping. So you can see here that if you sort of rigorously evaluate this pre-trained model over a variety of challenging terrains, it's actually not that great at a lot of them. But that still sort of does not prevent it from being really helpful as a starting point for fine-tuning. So in summary, we've seen that we can now have humanoid locomotion over challenging terrains, and we have this approach that consists of two steps. First, pre-training the model with sequence modeling, and then fine-tuning the model with reinforcement learning. That is the last slide I had, and I think maybe Jitendra can say
additional comment. So what is missing? So vision, exactly. So that's the next step, the final frontier. Can you do with a humanoid walking with vision, not just stairs, because I think stairs will not be that hard, but like stepping stones, right? Or parkour, or just in some unknown terrain, which is so essentially the way James Bond runs after a villain in a movie, okay, or Tom Cruise in Mission Impossible. You want your humanoid robot to be able to do that using vision. So that is left as an exercise to the gentle reader. Okay. And I think yeah. So we'll send you some links. I thought I would have a mini lecture on the approaches used by the folks in Boston Dynamics and MPC. So Scott Kundersma, Russ Tedrick, Mark Raber, that line of work. But I think we'll just give you references and you can read them yourself. Okay, so the lecture is over. Thank you.